Let's now look at this idea of integrating the derivative on the function. See, we don't integrate log x in extension 1 anyway. We'll see how to handle it in extension 2. But we will do this sort of problem. Basically, it's going back the other way. So if my integral is in the form of derivative on function, then I know when I go back, I must end up with the log of that function. It's going back. But here's the thing to note. It's actually the log of the absolute value of the function. The absolute value. Why? Well, because you can't find the log of a negative number. So when you go back, it needs to be the absolute value to make it a positive number. So I get 1 on 7 minus 3x. I would like derivative on function. Well, I don't have that. The derivative would have been minus 3. So I'll make it minus 3. Again, we can't change the question. So balance it out, we'll multiply by minus a third. It's now derivative on function, so I know that will go to the log of the absolute value of 7 minus 3x. Or minus a third times that, of course. dx on 8x plus 5, again we need the derivative on the function. The derivative of 8x would be 8. Balance it out, put an 8 out the front. It's in the form, derivative on function. So we'll go through the log of the absolute value of 8x plus 5. X to the 5 on x to the 6 plus 2, it's almost there. But of course the derivative is 6x to the 5, not x to the 5. So we'll multiply it by 6, but multiply by a 6 as well. And you'll notice I didn't worry about the absolute value. Well, that's because x to the power of 6 plus 2 is always going to be positive. Some people will put the absolute values in all the time anyway, just to make sure. But if you know that that function can't be negative, then you don't have to worry about the absolute value signs. You can just put parentheses around it. This brings up this. This is where integrating of functions that become logs gets really interesting, because you might do a problem like this. And you go, oh yeah, fairly simple, I've got the answer. You'll go and say, well, I better check my answer. You go to have a look at the answers and you say, hey, whoa, that's not what I got. Why is it different? Because you can get different answers. Look at this. 1 on 5x. I would like derivative on function. So that would be 5 on 5x. Balance it out, I'll put a fifth out the front. So I get a fifth times the log of the absolute value of 5x. But just imagine I did it a different way and said, oh look, 1/5 is just a constant number. I'll pull that out of the integral sign. And I'm now integrating 1 on x, and that is derivative on function, which means it's the log of the absolute value of x. You get a different answer. Now the thing is, it's not an issue. Let me just show you here why. They are in fact the same answer. It just doesn't look the same. Because 1/5 log 5x plus a constant, I could use log laws and rewrite that as 1/5 the log of the absolute value of 5 plus 1/5 the log the absolute value of x plus a constant. But 1/5 log the absolute value of 5 is a constant number. So whilst they've both got plus c, the difference between the two is the value of that constant. So it does not matter which answer we write. It just means, oh well, my constant will turn out to be something different depending on which one I use. Right? But as I say, when you're doing your exercises and you look up an answer, you might think you're wrong, but it doesn't necessarily mean you are wrong. You may well have a correct answer. 4x plus 1 over 2x plus 1. We would like derivative on function, but hang on a sec, how on earth am I going to turn 4x plus 1 into the number 2? And the answer is, well, I can't. So whenever we get this situation where the order of the numerator is greater than or equal to the order of the denominator, this one, it's the same. Do a polynomial division. Right, so rewrite it. Okay, whether you do a physical polynomial division or you can see it and just change it, this is what we get. So I could rewrite this as 2 minus 1 on 2x plus 1. Now the 1 on 2x plus 1 I can now rewrite as derivative on function, because I can change that 1 to a 2. And 2 we certainly know how to integrate. So it'll end up becoming 2x minus a half of the log of the absolute value of 2x plus 1. So when you see these sort of fractions, have a look and say, oh, hang on, what's happening with the order here? Okay, let's tidy that fraction up. Let's do a definite one. 2x on x squared plus 1. Oh, nicely, it's already the derivative on top. So we can go straight to the log of x squared plus 1. substitute in the 2, substitute in the 1, we get log 5 minus log 2, 5 on 2. A way you can save yourself a little bit of time. We're subbing into a log function. This is always going to happen. I'm going to end up with log minus log. Right? It's always going to happen. So I can always recombine it into one fraction. So if you want to write it straight down, you write it straight down and you just remember, well, I'll sub in the top number, that goes on the top of the fraction, 5. I'll sub in the bottom number, that goes on the bottom of the fraction, 2. It saves you one line, but it is possible to do that. Take care with the definite integrals though. You cannot integrate across an asymptote. What do I mean by that? Let's look at our hyperbola here, because there it is, derivative of a function. Imagine it said, what's the integral from minus 1 to 1? Now think about what integrals measure if we're talking about area under the curve. But you've got this asymptote here, which theoretically the curve's going infinitely up and infinitely down. How could you work out that area? You can't do it. So just keep an eye out for that sort of thing. You cannot integrate across an asymptote. Sometimes we'll see questions like this where they basically are giving us a clue or helping us out. Differentiate x cubed log x and hence go and integrate x squared log x. Differentiate x cubed log x, write down the first, x cubed. The second, differentiate log x, we get 1 on x, derivative on function. Plus, write down the second, log x. Differentiate the first, we get 3x squared. We end up with x squared plus 3x squared log x. And what you'll find in this sort of question is part of the answer, or all of the answer sometimes, is in fact what they're about to ask us to integrate, or a multiple of it. And we can say, well, yeah, we've got 3x squared log x, they want x squared log x. So therefore, what I know is if I've just differentiated x cubed log x and got x squared plus 3x squared log x, then when I integrate x squared plus 3x squared log x, I must get x cubed log x. Go back the other way. Okay. But that's not what I want. I want the integral of 3x squared. But that's when I look at it and think of it like an equation. So I'll move what I don't want to the other side, and that's the integral of x squared dx. It goes to the right. I'll factorise out the 3. We're allowed to factorise numbers for integral signs. And I now know 3 times the integral of x squared log x will be x cubed log x minus whatever the integral of x squared is. So that will become, when we divide everything by 3 as well, 1/3 x squared log x minus 1/9 x cubed. Now in extension 2 we'll actually see a technique that will allow us to do these sort of integrals without this massive hint. But at this stage, that's how they'll probably set a question up for us in extension 1. Differentiate this, hence go and integrate this. Alrighty, that'll do us. 6i and 6j.